So if there are any clarifications on the material we have covered so far, I can take a couple of questions now, because we have finished the discrete time models leading to the binomial model in particular, along with some simple illustration of how to price derivatives. But of course, I have shown you a much longer menu of possible derivative contracts, options, futures, swaps, everything. And for all of them, you need a corresponding computational algorithm. They are all based on, usually in the discrete time, they are all based on binomial models. So all you need to do is create an algorithm like the one that I shared with you on that website. And it's reasonably easy. So are there any questions regarding that part, the discrete time modeling part? All right, so if there are no questions on that, then I will move on to the continuous time models. So let me start by looking at the notes first, and then we will move on to other stuff. So our discussion today will be on the continuous time models in finance, and in particular we want to understand what is meant by a stochastic differential equation. All right, so before I move on to the actual discussion, I want to reiterate that I would like you to read the stochastic process notes that I shared with you earlier, particularly the MIT lecture notes, and also whatever textbook you are familiar with, because some of the stochastic process material are not familiar with all of you. So in particular, I would show you this lecture note. This is the lecture 13, no, lecture 17. Lecture 17 from this MIT course, and this is specifically related to continuous time stochastic process. So if you want to brush up, if you want to revise, or if you just want to pick up the basic concepts in summary, this is a very good reference. So this has got most of the background material that I will be needing. So it's a good idea if you go through this. So let me then come to my main agenda. So what's my main agenda? My main agenda is to understand, to begin with, to understand what is a stochastic differential equation. We all know what is a differential equation, and now we have some idea about what is a stochastic process. These two things together will now help us create some object called the stochastic differential equation. We'll first understand why we need it, and then we will obviously try to find out how to solve those kind of equations, and then finance applications. So our canonical model is the population growth model. So let's start with the population growth model, because this is a model all of you have seen before in the demography course or in the applied stochastic process course. There are various platforms where you have seen the population growth model, and a typical simple model is, if the population size is nt at time t, then the model is dn dt is given by at nt, where at is the growth rate. At is called the growth rate, and our time zero value n0 is assumed to be a constant. That's the canonical population growth model, and we know how to solve it. It's very easy. Now, suppose I want to go further. I want to allow for some uncertainty in the growth rate. So basically, I want to allow uncertainty in AT. So AT is a function of time. I also want to make it a random variable. In other words, I want to make it a stochastic process. It's time dependent, and I want to make it uncertain. So the resulting differential equation will look like dndt equal to AT&T, where AT is given by some RT, which is the trend part or deterministic part of the growth rate, plus some noise. We will make this more precise. Now I'm just writing it in simple English, but we want to make it more precise. But conceptually, this is a differential equation involving stochastic coefficient. And this is what we call a stochastic differential equation. This is one particular stochastic differential equation which we want to understand, and in the process we will also understand more general facts. What is our target? So our target obviously is finance, because we are doing math finance here. And in finance, pricing of the derivative contracts in continuous time is most commonly done most commonly done using the Black-Scholes model. So the Black-Scholes is due to Black and Scholes. These are two persons. They developed this option pricing differential equation in 1973 using a very fundamental result in stochastic differential equations, which is known as Ito's lemma. Now, Ito was a pure mathematician who didn't have any idea about finance, but he developed a very nice tool for solving the stochastic differential equations back in 1951. And then obviously no one outside the mathematics community knew about it. Black-Scholes essentially in the late 60s and early 70s rediscovered Ito's lemma. And they found a very nice ingenious way of using it for pricing options. And that gave rise to a huge literature in mathematical finance in continuous time. All sorts of derivative contracts could be priced, and they were priced using the basic Black-Scholes model. Of course, over time, the model has been expanded. It has been extended to cover many other cases, many more generalities. We will discuss some of them after we understand the basic model. But the backbone of this whole literature is the Black-Scholes option pricing model, which is again dependent on the Ito's lemma. So for us, it will be first very important to understand what is the background that leads to the Ito's lemma. That's the mathematical background, which is common to any such stochastic differential equation scenario, not particularly in finance. And once we understand the background leading to the Ito's lemma, then we will of course specialize and move on to Black-Scholes, and there our applications will be purely based on the financial contracts that we have discussed so far. So there are two steps here. The first step is a general step, applying some mathematical tools for a variety of issues. And the second step is more specific, where our issue is in particular financial contract pricing or derivative pricing. Now, when you have a differential equation, you certainly do have a time-dependent function as a solution of the differential equation. So you know exactly what should be the value of nt at time t once you solve it. If your differential equation has some stochastic coefficient, like the one we are talking about here, then you really cannot expect to find out a deterministic function of t, of course, because then the uncertainty would be completely irrelevant. So what do we actually hope to get? We actually hope to get another stochastic process. So we start with an input stochastic process, AT, or the noise. The noise we will model more specifically. The output will also be a stochastic process, NT. So what we really can tell about NT or NT omega, if we are able to solve it, is what is the distribution of nt omega at time t. So instead of having a deterministic function, we will have a probability distribution at each time. Is that clear? Is this context clear?
Yes, sir.
Yes, sir.
Thanks. So basically we are first going to understand what is this nt omega, how to formulate it specifically in terms of the noise. We have to make it precise, and then of course we will use it for our special purpose of financial contract pricing. Okay, so just to reiterate, now that we are in continuous time domain, we are going to define a stochastic process again. A stochastic process is a parameterized collection of random variables. These are indexed by t, time t, which comes from an index set capital T. And the sample space is omega. The corresponding filter is script f. And of course, we have the corresponding sequence of filters ft, because we are eventually going to talk about ft adapted processes. So that will be created out of the filter and the probability function p. So the typical triplet omega fp, and we are assuming that it's a real valued function because for all our practical purposes we are going to talk about price, so it's a real value. And also because we are going to talk about time specifically, so we normally will consider t as r plus, which is the positive reals. So all time from 0 to infinity, that is one possibility. Or we may want to specialize to a finite interval of time, generically called a to b. Typically we will call it 0 to capital T. So 0 is our initial date and capital T is our expiry date. For most of the contracts there is an expiry date, so we have a finite interval. Or if we have some perpetual contracts, then we can think about the whole of the positive reals. Right. So now, again, just to repeat, we think of the stochastic process as a random variable if we fix time, and a sample path, which is a deterministic function of time if we fix omega. So for any omega, it's a deterministic function of time, which is a sample path. And for a fixed time t, it's just a random variable. That's how we want to see a stochastic process. And this dual nature is going to be used very, very often. So I just wanted to repeat this point. We want to specialize to certain nice classes of stochastic process to make our life easier. So what are these nice classes? These nice classes are going to be defined in terms of what we call a second order process. So we say that a stochastic process is a second order process if the variance is finite for all t. So expectation of x square is finite for all t in the index set. That is a second order process. You understand why we want this? Because we want finite variance, because like in the discrete model, we went to the binomial distribution. In the continuous model, like any nice statistician, we would like to go to the normal distribution. And normal distribution is parameterized by the mean and variance. So to begin with, we do not want to mess around with any process which does not have a variance, because that will be very hard to begin with. Of course, later on we will talk about other things, but this is the starting point. A bit of notation, we call the mean function mu as usual, mu xt. Mu xt is the expectation of the process at time t. A covariance function gamma x st, which is autocovariance, covariance between xs and xt. And of course, variance is gamma xt. That's our generic notation. If we want to talk about correlation, we will use the symbol R, and this autocovariance function, we will use the symbol gamma. And mu is always our mean. And again, if we want to talk about variance, we will use the symbol sigma. That's the usual tradition. Now, because we have started using covariance and variance, it is also nice to note that our linearity, the linear combination rules will all work in this case. So we can talk about linear covariance between linear combinations of these random variables, and because of the linearity properties, they will be nicely structured. We will use them because, as you know, we are going to move to normal distribution and we want all those nice properties. So what is our fundamental building block? Our fundamental building block leading to the normal distribution is called a Gaussian process. What is a Gaussian process? A Gaussian process is a stochastic process for whom every finite linear combination of those xt's will be normally distributed. So you take any linear combination of xt's, they will follow a normal distribution. That is the definition of a Gaussian process. Again, some of you are obviously familiar with the Gaussian process, but if you are not, I have just showed you the basic material which you can look at, and also the nice textbooks that we have talked about. In particular, I would like you to look at Whale-Port Stone or Ross, because they are very nicely written if you want to brush up. Or for a quick recap, you can look at the MIT lecture notes. Okay, so a Gaussian process, all linear combinations, finite linear combinations are normally distributed. We also talk about the Wiener process or Brownian motion in this context, because that is the most celebrated model in this literature. So what is this Wiener process or Brownian motion? This is like a movement of a particle in some medium. So let me show you this website first. So this is again the Brownian motion simulator, and the link I have already shared with you in the website's page. In the website's page, if you can see this one, here I have this Brownian motion and random walk simulator, which I have opened on my browser. And here you will get some background. The background is not so important. What is more important and what is very interesting is how do Brownian motions look like. So these are simple examples using the coin toss experiment. So this is a random motion from coin toss, where at any point of time you can either move up one step with probability half and move down with probability one step with probability half. But yes, is there any question? So this process is our fundamental building block. If you do this for a long interval of time, you will get this kind of patterns, and these patterns are typically associated with the Brownian motion. Even though the generating process here is a discrete one, coin toss, but if you look at it for a large number of time steps, you let the number of time steps go to infinity, then this has all the properties of a Brownian motion, which is in principle related to the Gaussian process. If I want to look at it in a two-dimensional space, then this is what you will get to see. Now on your screen, here is a two-dimensional Brownian motion, a two-dimensional random walk being generated. And Brownian motion can be actually defined in terms of a limiting version of the random walk. Are you familiar with this result? That you create a random walk from coin tossing, and then you go through a limiting process which will give you the Brownian motion. Is this familiar?
No, sir.
Hello?
No.
No, sir.
No, sir.
No, this is not familiar to you, right? Okay, so later on we'll discuss this a little bit more in detail. But for now, let me just give you the analogy. The analogy is simple. You all know that if I have a binomial distribution and if I increase the number of trials, then the distribution will approach the normal distribution. This you all know, correct?
Yes, sir.
Yes, sir.
So it's the same thing here. So if you look at a random walk is nothing but where you take a step upwards 1 unit with probability half, or take the step downward 1 unit with probability half. So it is like a Bernoulli trial. It's a coin toss experiment. And accordingly, you either go up or you go down. What is happening in this one-dimensional example here? So this is a Bernoulli. So if you aggregate it, you will get a binomial distribution. So you know that the limit, when you let the time steps go to infinity, the limit will be a normal distribution. So in the stochastic process scenario here, in these graphs, it will lead to what we know as the Brownian motion. Again, Brownian motion is very much linked with normal distribution, which we will see shortly. So that's how the limit works. If you want to see how it works formally, you can look up Ross or Well-Portstone. There are simple proofs, or we can discuss this later. All right.
Yes, sir.
Okay. So now you should take a little bit more time later on and look at these simulations, because not only the simulations are here, but also the codes are here. This is a MATLAB code, but of course, if you are not familiar with MATLAB, you can just rewrite it in R or Python, whatever you are comfortable with. So this code will generate random walks for you. Okay. So let me go back to my notes. So I have defined the Gaussian process, and I wanted to understand what is the Wiener process or Brownian motion. So in physics, people think of this as movement of a particle in some medium. So it is like, if you want to create an analogy, you can say that it's the position of particle omega. So you relate particle with omega at time t. Because we want to understand this as a stochastic process, we have xt omega. For physics, physical motions, you can think of omega as a particle. So that's the usual physical description of the Brownian motion. What is our mathematical description? Our mathematical description is a process Bt, where t is indexed by the positive reals, that satisfies. It starts from 0. The initial value is deterministically set at 0. So you start from the middle. So the difference of the values at time t and time s follows a normal distribution with mean 0 and variance proportional to the time interval. So the variance, see, this is very important. We will use, and we will understand this more a little bit later, that the variance is proportional to the time difference, time gap. So Bt minus Bs follows normal 0. Sigma square is some scaling constant that we can estimate. Sigma square times t minus s. If it's a standardized Brownian motion, then we will just take sigma square equal to 1, as in a standard normal distribution. And also, the differences over disjoint time intervals are independent. So if I'm looking at time points t1, t2, t3, then bt2 minus bt1 will be independent of bt3 minus bt2. So increments over disjoint intervals are independent. So is this clear? This is mean 0 because I have the same chance of going up and down. So in expected terms, I will stay at the same level. The variance is proportional to the time gap. That is very important. And increments over disjoint time intervals are independent. So is this clear? The definition and what it really means?
Sir.
Right. So again, the first straightforward consequence of this definition is that the Wiener process of the Brownian motion is also Gaussian. Okay. Is that clear? That the Wiener process is also Gaussian?
Yes, sir.
Can you just confirm that this is clear? Because I said that the differences follow normal distribution, and now I am claiming that all finite linear combinations follow normal distribution. But
Just in case as 0 and then V0 is 0.
you can see the connection, right?
Yes, sir.
Yes, sir.
Very good. Good. So that is a very easy thing. So I don't even call it a result. I just note it that a Wiener process is also Gaussian. So these will be our building block. Just like in statistics for the last 4 years, you have been always trying to work with normal distribution. In our financial derivative pricing theory, we will always try to work with the Brownian motion. And the reason is obvious. We know a lot about normal distribution. Okay. So now a little bit more of the nuances. Before I move on to the results, what I want to understand is something called a path continuity. So let us understand what is that. So what is continuity for us? So suppose my t, which is could be the whole positive real line or any finite interval of the real line, it's uncountable. So when t is uncountable, then these processes are called continuous parameter process. So the parameters are assumed to take values in a continuum. Now I want to focus on some more assumptions or some more properties which will make our study of this process easier. So I make a second definition. So let xt be a second order and continuous parameter process. Second order means variance is finite for all t. We assume in addition that the mean function mu x is continuous function of t. So the mean function is a continuous function of t, and the covariance function gamma xt, gamma x st is jointly continuous in S and t. So we make these two assumptions. We want to make our life easier. We want to have some smooth properties. So we assume the mean and the covariance function to be continuous in time. And then you can easily check that this will mean that the process shows mean square convergence. So if I look at the squared difference, xs minus xt whole square, take its expectation. So this is the expected squared difference. And then I take limit s approaching t. So I consider time points who are close to each other. Then this limit is 0, which means the expected mean square difference goes to 0. And this is known as mean square convergence. Mean square convergence you must have studied before in some asymptotics or estimation theory course. Is mean square convergence known?
Yes, sir.
Because you have done this mean square error kind of calculations before for good estimators. So this comes directly from estimation theory. It's the same thing. So mean square convergence is this property which one can show, which follows from the second order property and the continuity of the covariance function. So if I have continuity of the covariance and the second order property, those nice things, then I have mean square convergence. So that is one point. So now this is the first part, because this part is completely involved with the timeline. So I want to understand continuity along the timeline. what about the sample space? Do I have a corresponding smoothness property in the sample space? In particular, can I make the sample paths continuous? Because if I fix an omega, then each xt omega is a function of time. I have talked about the continuity of the mean function, covariance function, etc., and the mean square convergence, but that is all in expected terms. But can I say something about individual omegas? That is not so easy to assume, right? Because assuming continuity for each omega is a lot of assumption. But suppose we make that assumption. Can we justify that? So, of course, if we make that assumption, life would be easier later on. But justifying that assumption would be important because we are making an assumption for each omega, and you understand it's a lot of assumption. So let us first take the assumption. We assume that the sample paths are continuous for each omega. But is it assuming too much? That's the question. Or in other words, am I restricting too much in the sense that all the real life processes will not justify this assumption? Because then my assumption is a bad one. Okay, so let us try to understand that. So I have this following definition where I say that xt and yt be two stochastic processes on the same triplet, omega fp. We say that xt is a version of yt if their probabilities are identical. So they coincide with probability 1. So again, some of you who have done stochastic process formally must have come across this definition before. If you have not, then all I am going to say is that, well, there are formal definitions, of course. This is not a formal definition. All I am saying is that xt and yt matches in probability everywhere. So it's a probability matching. They don't have to be the same object, but they match in probability everywhere. So the probability of all the omegas where they are equal, that has probability 1 for every t. Do you understand this definition? And also why I am saying that they need not be the same objects?
Yes, sir.
Because it's a little bit of a nuanced idea. That XTYT could be coming from completely different kind of measurement processes, but if they probabilistically match, then that's all we are interested in. In fact, in probability, we have a similar result also, where we say that X and Y are identical in probability. Because in probability, that's all we are interested in, the probability distributions. So here also I am saying that for each t, they are probability distributions. For each t, they have the same probabilities. Okay. So why is this definition relevant for us? Because we were discussing continuity of sample paths and whether we should make that assumption. It is relevant because of this very important and extremely fundamental result due to Kolmogorov. So it's again one of the benchmark results in stochastic process, Kolmogorov continuity theorem. What is the statement? So suppose xt is a stochastic process satisfying the following. For all t strictly positive, I have three constants, alpha, beta, and capital D, such that the expectation of this powered absolute difference, xt minus xs modulus power alpha, this particular expectation is bounded above by d times t minus s power 1 plus beta. So it is, if you have done a differential equation course, it is somewhat similar to a Lipschitz type condition. But you don't really need to connect it with Lipschitz. What you are really looking at is essentially how fast the differences grow in expectation. So these are basically differences. So how fast am I allowing the expected difference to grow? It has to be of this order in time gap. So Kolmogorov proved that if my xt satisfies this condition, so if I can find some alpha, beta, and capital D so that this is satisfied, then there exists another stochastic process yt which matches with xt in probability as in this definition. So yt is a version of xt and yt is also continuous, which means yt has all sample paths continuous. So even if xt does not have continuous sample paths, if xt satisfies this particular boundedness property, I can always find a version of xt and yt equivalent in probability to xt, which has continuous sample paths. These are called continuous versions of a stochastic process. Is the result clear? Is the result clear to all of you?
Yes, sir.
And I claim that for Brownian motion, this condition holds. Can you tell me what is the corresponding alpha, beta, and capital D for Brownian motion?
Alpha will be 2, beta will be 1,
Alpha
0.
2. So you are looking at variance, and beta will be
0.
and D will be what?
1.
Okay, for standard normal, this will be 1. All right. Okay. Any other candidates?
For alpha equal to 1, D will be
Well, just saying something about
alpha equal to 1, D will be 0.
for odd numbers, the result might be complicated. Try even numbers. Alpha equal to 2 is easy, so try even numbers, because then your modulus will not create any trouble. Do you see that alpha equal to 4 will also give a bound for normal distribution?
Yes, sir. So alpha equal to 4, beta equal to 1, and D equal to 3.
Right. So it's the Kurtosis condition, which will also hold for normal distribution. So yes. So then we are sure that for Brownian motion, Kolmogorov continuity theorem assumption holds. So this condition holds. So we know that if I am talking about a Brownian motion, then I can always assume that it has a continuous version. I don't need to assume. Then I know that there is a continuous version. So whether the original Brownian motion has continuous sample paths or not, it doesn't matter, because all I am interested in are the probability distributions. So what I will do is I will take the corresponding continuous version using the Kolmogorov's theorem, and we will work with that continuous version only. So we'll forget the original Brownian motion. We will take the new Brownian motion, which is equivalent in probability, but has continuous paths. Okay, so in probability terms, I am doing nothing. All I am saying is I can always safely assume that the Brownian motion I am working with has continuous sample paths. Is that clear?
Yes, sir.
So basically we are working with a stochastic process which is second order continuous parameter, which has this nice nice continuity of the mean and covariance functions. And I also know that if I'm working with the Brownian motion, then I also have continuous sample paths. So because these assumptions are so convenient, I have clubbed them together and I call it assumption capital A. So later on, if I say that, okay, let us talk about a process satisfying assumption capital A, then it will mean all of these things. So capital A is a set of assumptions and we have talked about them separately. Later on, we will just invoke them together and say that take the process as following satisfying assumption A. Okay, so this is a small property that I want to mention here. It will be very important later on, that for a Wiener process, if I look at the expectation of this kind of a cross product, Bs minus Ba, where A is the initial time point, times Bt minus Ba, this will have this value sigma square times minimum of T minus A, S minus A. Is this result clear? Because we have already said that increments over disjoint intervals are independent. So basically all I need to do is take the common part, which is minimum of T minus A and S minus A. There it will be the variance, and that variance is sigma square. If you are talking about the standardized version, then I will just take sigma square equal to 1. Okay. Is this result all right?
Yes, sir.
Because then we are on our way to define our stochastic differential equations. So we have the necessary theoretical background. We have understood the basic building block, which is the Brownian motion or Wiener process, and its connection with the normal distribution. We have understood the continuity properties, which will be useful later on for proving results. And in addition, we have this independent increment property from normal distribution, which will help us in doing calculations. Many of the calculations will get simplified. So,
Sir,
yes.
sir, can you once again explain the implication of a version of a stochastic process or a random variable?
Okay. So this definition is the basic premise. So what I am saying is, I have two stochastic processes. If their probability distributions match at each time point t, then I say that these two are versions of each other. So probabilistically, they are equivalent. So
Their values can be different, but they are identically distributed.
their values can be different with probability 0. You see, the requirement is the omegas where they match, omega such that xt equal to yt has probability 1 for all t. So they may not match in some places, but those places must have probability 0.
So what is the implication of this version?
What is the implication?
Of version. I mean, why do we need this? Like, we could have worked with the Brownian motion itself. So why are we taking its version?
Oh, no, 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 no. Brownian motion is a very nice stochastic process, and using this Kolmogorov continuity theorem, we can show that it has continuous sample paths. But to invoke Kolmogorov continuity theorem, I need this definition. You see, just from the definition of Brownian motion, there was no guarantee that all sample paths will be continuous.
Okay.
So that's why I said that it's a bit of a nuanced point. We are actually interested in these continuity properties here. For a Brownian motion, I know that these first half, which is function of t part, the first part is true. We can do it, we can show it by direct calculation. But this is the last part here, the second part, continuity of sample paths, that requires a bit more work. And that work is based on this definition of a version and the Kolmogorov continuity theorem. I need to know that I can actually invoke the continuity theorem to prove that Brownian motion has continuous sample paths, or Brownian motion has a continuous version. For all practical purpose, you can rewrite this result as saying that because of Kolmogorov continuity theorem, Brownian motion has continuous paths. If you want to be very precise, you will say that Brownian motion has a continuous version.
Okay.
Does that clarify matters, or are you getting more confused?
No, sir.
Yes, Pushmit?
Yes, I have understood.
Yeah. So basically the version part is a very nuanced probabilistic conceptual point, which for the time being you can ignore, just thinking of this as Brownian motion having continuous sample paths. That will not create any trouble in terms of our calculations and results. But it is good to know that it is actually a little bit of a difference, because versions need not be actually identical as mathematical objects, but probabilistically they must be identical. There is a little bit of subtle difference there. All right, so I guess it's a good point to take a break. So I will take a break, and let us resume at 11:50 maybe. It's 11:21, so we can start at 11:50. Okay, so let me begin. So we stopped at the Kolmogorov continuity result, and we now know that the Brownian motion has a continuous version. Now we want to move on to the construction of the integration theory, which we need to solve the differential equation that we have notionally written. All right. So what is a very natural occurrence of integration in statistics? If you are looking at a continuously recorded data, so data that is recorded continuously in continuous time, so then a sample of that data will be xt in some interval a to b. That will be a sample data for you, for us. And based on that sample data, if I want to find out the sample mean as an estimator of the population mean, mu, then this would be our candidate. Our candidate for sample mean would be mu hat, given by this integral divided by the length of the interval. So this is one natural occurrence of integration in statistics. And when we talk about continuous parameter stochastic process, then the corresponding data that we can think of is also a continuous parameter time series. In the discrete domain, it's a natural candidate. When we have a discrete parameter stochastic process, the corresponding sample is a usual time series, as we know, discrete time interval time series. But when we are looking at continuous parameter stochastic process, there also we have an analogous sample, which will also be like a time series, but now the index set t will be from a continuum. So am I making sense here? So I'm just trying to connect the stochastic process in probability with its sample counterpart, which in discrete time is time series. Is that point clear? Is that connection clear?
Yes, sir.
So now if I am talking about continuous parameter stochastic process and I want to do similar statistics, then I would be, at least intuitively, I would be using some kind of integration to find out estimators. So estimation naturally leads to a requirement for an integration for stochastic processes. Because if the sample version is an integration, then to understand the property of that, I will need to understand the property of that integral when the integrand is a stochastic process or a random variable. And that is exactly the same requirement as in to understand how to define and solve a stochastic differential equation, because that will also require integration of a random variable. And that integration we now need to define, we need to understand. So again, as I said, we have that group of assumptions A. So we assume that our stochastic process that we are studying satisfies A. So all the assumptions in A. For any fixed omega, if I am fixing the sample path, then I have the usual integral defined in the usual way. So I can define an integral like a to b ft, where ft is any deterministic function of time, xt omega dt. So there is no ambiguity in understanding what this integral means. Because I have fixed omega, there is no further uncertainty. It is only a function of time. So integration, as in the usual Riemann integral, is well defined. And we know how to do it. We have learned it in our undergraduate first year. The challenge is to extend this definition, extend this concept to a stochastic situation where we also need to allow omega to vary. So we need to allow for uncertainty. And that is the famous Ito integral. So I already mentioned Ito's lemma, the result on which the Black-Scholes result was based. But what Ito really developed was a full-blown integration theory. So it is not only a simple lemma, it's a full-blown integration theory. And the Ito's lemma is one part of it. We will get there. We haven't yet talked about what the Ito's lemma is about. But what we are now going to discuss is the integration theory. And in particular, we will talk about the integration theory according to Ito. Why do I say integration theory according to Ito? Because already for usual classical calculus, we know that there are different integration theories available. The integration theory that we learned in our first year informally and then later on formally is the Riemann integration. But that is not the only possible candidate for an integration theory. As we go ahead in our later years, we also learn about Riemann-Stieltjes integrals. When we learn measured theory, we learn about Lebesgue integral in integration. So I don't know how much of this is already familiar to you, but I'm sure that by now, all of you know that Riemann integration is not the only candidate for an integration theory. Am I right? Have you all?
Yes, sir.
Yeah. So you at least know Riemann-Stieltjes integral, I think, isn't it?
Yes, sir.
So have you also come across this Lebesgue integration as in measure theory yet, or are you going to learn it this year?
We had it last year, sir.
So yeah, okay. So
Stream has measure theory compulsory last semester, but the NPs do not. So not all people know Lebesgue integral.
right. So I guess then the question is that the students who are coming from the NB stream, do you have any idea about integration theory other than Riemann integration? Can any of you respond?
Some of us have had major theory in our second semester, so they probably have knowledge.
So was that an elective course?
Yes, sir.
Oh, I see. I see. So anyway, I am not going to use the formal theory much, and whatever I am going to use, I will develop for myself in an intuitive way. But because we are talking about stochastic process, I am going to develop the stochastic integral. I am not going to talk about the deterministic integral. So when I define this theory of integration, it will be in the nature of a random variable. But if you are following it closely, you are following it clearly, you will see the connection with the other integration theories as in the classical calculus. But that is not necessary. It would be nice if you can find the connection, but it is not necessary. But anyway, let me start the discussion and then we'll see how we go. So the construction of this integral is essentially to find a reasonable interpretation for the noise term in our differential equation. You recall the equation 1, the very first equation that we wrote up there in the morning. So in the morning, we had this first equation. This was our equation 1. And there we introduced a randomness in the growth coefficient. So that's the equation I am talking about. Now, I can think of a slightly more general form of this equation as in equation 2. So our first objective would be to understand how to find out a solution to the second equation. And you can see that if I can analyze equation 2, then equation 1 is automatically done. So our candidate equation will be dx dt equal to b txt. So this coefficient b will depend on time as well as the value of x at time t plus sigma txt, which is like our variance into noise. So this is the equation we are looking at. For the growth model, btxt explicitly had this nt. Okay, so is the equation clear? So this is the equation that we are considering. And I claim that if I can solve this equation, the first equation problem is also solved. Is that okay? So the first question that I need to answer is, how do I model the noise? And of course, by now we all know that we will always try to somehow get to the normal distribution. As in our age-old regression model, our epsilon, the error term epsilon, used to follow normal 0 sigma square. So here also our objective would be met, hopefully will be met, if we take the Brownian motion as our noise process. But before we make that choice, we want to mention a few of the desirable properties that we will be needing later on. To develop the full integration theory, we will need certain properties. So let us start with the discussion of those properties and then see whether Brownian motion is going to work for us and also whether there are other candidates. Okay, so to find a reasonable candidate for our noise term, the desirable properties are the following. So what do I want? So if my noise term is Wt, so now let us use W as in a generic way. So it, of course, we know that eventually Brownian motion will be a candidate, but we also want to understand whether there are other candidates. So for the noise term Wt, what we want is, which would be very useful, is if Wt and Ws are independent for S not equal to T. This is in the spirit of the IID noise term. The independent, identically distributed, and of course I want a stationary distribution. So have you come to the stationarity in time series yet?
Yes, sir.
Yeah, so you know what is a stationary distribution. Great. So for stochastic process, you have the analogous definition. So I want a stationary distribution because otherwise there will be a lot of things to estimate. If it is stationary, then I have clear mean and variance, etc. And I want it to be mean zero. I want it to be mean centered. So I want expectation to be zero. I want the process to be stationary, and I want the process to be independent at different time points. So these are very desirable properties for me, and you can see the analogy from the usual regression models. Now the first result or theorem is a negative, is a bad news. So what is the bad news? If I take a continuous parameter second order process Vt with the following properties. So I want these properties. What are the properties? Vt and Vs are independent for S not equal to T, which we have in the desirable set. Vt is continuous in mean square, that we have already wanted to happen. Earlier we took that assumption capital A, and we want it to have bounded variation, of course, and we want it to be mean centered. So expectation of Vt should be zero. So we took the independence, we took the mean centering, and along with stationarity, we are actually asking for something more. We are asking for continuity in mean square and bounded variation. All of these sounds quite reasonable requirements. Trouble is, if I assume all of these things on Vt, then Vt has zero variance. So the first result that we come across here is an impossibility result, that if I want an otherwise nice set of properties to hold for the noise term Vt, then Vt cannot be a proper random variable. So is the result and implications clear? Because this will actually give rise to some compromises. Obviously, you understand, if we cannot have all the assumptions, we will have to let go some of the assumptions. But is the result and its consequences clear? Just take a look at this carefully. I wanted some desirable properties here, and I added to that some of our properties from capital A assumption, bounded variation, convergence in mean square, etc. As soon as I put in these assumptions together, I do not have a candidate. So this is my impossibility result. Is the result clear?
Yes, sir.
Are the implications clear?
Yes, sir.
Good. So whenever we have a set of assumptions leading to some contradiction, so this is a contradiction in the sense that all of these properties cannot hold together. What we need to do is, we need to go back to our list of assumptions and see which one we can let go, because we have to compromise. We have to give up some assumption and see if we have a possibility. So to come out of this impossibility, we have to give up one or two assumptions. So that's what we are going to do. So now for the construction of our Ito integral, we have these requirements. As I said, these are very natural properties. Independence, mean centering, continuous in mean square. And with that, for nice stochastic processes, we added the finite variation. Okay. So these are the things that we had to begin with. Now, when we had the impossibility result, then people actually thought that, okay, which one can be safely given up? We have to give up something. So which one should we give up? So the candidate choice that was made is that let us give up finite variation. To begin with, let us allow V to have infinite variation, possibly infinite variation, and then see whether we can still make sense of the stochastic differential equation, and from that an integration theory can be developed. Now, giving up finite variation is a serious problem because that means we have infinite variability in the random variable. That will might create a lot of trouble in our construction, because we are, in general, we always bank on having a variance, finite variance kind of thing. But this was the choice that was made, that you give up the finite variation and you look at this equation, which is equation 2, in a slightly different way. Because we know that there is no finite variation in V. So if I write it in the usual way, dx dt, and I put Vt here in the noise term, which is here also, then I have this problem of infinite variation. So can I express it in a different way so that it makes sense and I can go ahead with the integration theory, developing the integration theory. So to do that, we go back to first principles. So what is the first principle that we go back to? A differential equation is nothing but a limiting process of a difference equation. So let us write the corresponding difference equation here. So we write the differential, or the difference, xt plus h minus xt equal to this way, fxth plus order of h. So it is like our first order Taylor series. And we have to propose a good stochastic part candidate for fxt, because we know that in fxt there is deterministic as well as stochastic part. Otherwise, it will not be a stochastic differential equation. So the rate of change, which is fxt here, must have some stochastic part. So what do we propose here? So we do the easy thing. We take the deterministic part and call it fxt again. So that is a bit of an abuse in notation, but you can understand. So fxt is now the deterministic part, and we model the stochastic part of the increment as a difference in V, Vt plus h minus Vt. So to incorporate randomness in the increment, we invoke our V function. So Vt plus h minus Vt is a candidate for the stochastic part, and then of course order of h. So what do we have? We have our candidate Vt with independent increments. So we can also specialize to normal distribution, which would give us a lot of leverage, because I know that if I can somehow get to the Brownian motion, I have a lot of ready-made results. So our candidate is like this, that Vt plus h minus Vt, let us assume that the conditional distribution of this increment given xt follows a normal distribution, so that we can actually use the Brownian motion or the Wiener process. So if I assume the normal distribution, I can use the traditional notation and say that this increment is same as sigma times wt plus h minus wt, because this is our canonical normally distributed process, Wiener process. So I take this one as my error part. So in the original increment equation, I now have the trend part fxth, and this v difference of v part is now going to be written as a Wiener process difference. So then from that equation, I can immediately say that expectation of the change, expectation of xt plus h minus xt, will be given by fxth plus the order of h term, which we have ignored. And variance will be exactly given by sigma square times h. Okay, because the variance is same as this sigma square variance of this increment, and we know that the variance of this increment will be same as the length of the time interval, which is h. So the variance is sigma square times h, expectation is this. Why are these two important? Because after all, I'm talking about a normal distribution, and for a normal distribution, if I know these two moments, I know everything. Clear? Is this okay? Is this representation clear to you?
Yes, sir.
So I start from first principle, write it as a difference equation, then introduce the randomness here. And for the randomness, we use the particular candidate of the Wiener process. So I know the mean and variance of this increment, and I don't need any further moments because I am using normal distribution. So now let us take the limit and write this difference as a differential. That's how we define a differential equation. We start with a difference equation, take the limit, and then the difference becomes a differential. So the formal expression will look like this. The formal expression will be dx equal to fxt dt, which is the trend part or the deterministic part, and sigma xt dw. Now this symbol dw is nothing but the limit of this difference here. All right, is this representation clear? Now, question. If I look at the dx expression formally here, what happens to the variance? Recall that dx is also a random variable because there is a stochastic part involved. So what happens to the variance? What is the order of the variance here for dx?
4.
Can somebody say what is the order of the variance here? For the difference equation, the variance was given by this expression, sigma square times h. Now when I am writing it in the differential form, what would be the order of the variance?
Zero.
It will go to 0, but what is its order? Can you match it with some other order in this equation? So what is the limiting candidate for H? So when we wrote the differential equation from the difference equation, H got replaced, right?
So variance will be of order dt.
Variance will be of order dt, because in the difference version, variance is of the order of H. So now, suppose I wanted to go back to the original equation 2 and wanted to find the variance of dx dt. Can I find it? What would be the order of the variance of dx dt?
T square.
Come again? What would be the order of variance for dx dt? Because originally we were talking about dx dt, but then we sort of changed track and came to dx. So can you tell me the variance of dx dt? Anybody? If you just mechanically try to calculate the variance of dx dt, what will you get? So we have already said that variance of dx is of the order of dt. So if I divide it by dt, if I divide dx by dt, just think of this as a mechanical division. What would be the order of the variance?
O of one and constant.
Huh?
O of one kind of.
One.
0.
0.
E of 1 by t.
It would be 1 by t. So we have a lot of candidates, 0, 1, 1 by t.
dt inverse.
dt inverse, it's 1 by dt. If you just look at it mechanically, then variance of dx is sigma squared dt. Okay, let's look at that. Variance of dx is sigma squared dt. This we know. Now I divide dx by dt, which means the variance will be divided by dt whole square. So then I will get the expression sigma square by dt, correct? Just think of it as a mechanical division. So this the variance of this object will be of the order of 1 by dt. And you understand what will happen if I take the limit. And that's why this infinite variation clause was inserted. The reason that we got a solution is we gave up on the finite variation part. And the consequence is the solution in the ratio form will have infinite variation. So dx dt as a random variable is not a proper random variable. If I want to find the variance of dx dt, I will run into trouble. But I can make sense of the symbol dx. Dx is manageable. but I cannot divide by dt on both sides. Is this clear? This is actually a very deep point in this stochastic process theory. I am just giving you an informal version of it, but the basic problem should be clear to you. The basic problem is that of whether we are able to maintain finite variation, whether we are able to guarantee finite variance. If I write the equation in the ratio form the way we are used to do, it will have infinite variation. But if we write it in the differential form, then I am better off, because then the variation can be controlled. So is this clear? So I will just go back up and reiterate this, because it's a subtle point that I wanted to make sense of this stochastic differential equation, and I need a reasonable candidate for noise. I initially proposed some desirable properties. Along with that, we added the capital A assumptions with continuity in mean square and bounded variation. The trouble was, all of these things together do not give me a proper candidate, do not give me a proper random variable. Then I will end up with zero variance. So I needed to give up something. So what do I give up? We gave up finite variation, which would potentially mean that the symbol dx dt will have infinite variation. But okay, we can see what happens. So we gave up finite variation, and then we rewrote our equation in a difference form and inserted the Wiener process in the stochastic part of the change. So this is the change equation, fx and v, difference of v. So we inserted the Wiener process to introduce normality, normal distribution. Once we have that, we can calculate the expectation of and variance of the difference here at the increment. And then we take limit, we write it as the differential form. So the differential form will formally look like this equation here. For this equation, I know that dw has a variance of order dt, because in the difference form, the variance was of order h, which means the variance of dx will also be of order dt. Now let us connect it with the infinite variation problem that I mentioned earlier. If I now mechanically look at this ratio dx dt and try to calculate its variance, I will get an order of 1 by dt, which will explode when we take the limit. And that is why this infinite variation had to be allowed in dx dt. So if we wanted to use dx dt, we had to allow infinite variation. But working with infinite variation is impossible. We cannot do any probability calculations there with any good model. So to allow infinite variation in dx dt, we stop using the ratio. We stop writing the differential equation in the ratio form, but rather we write the differential equation in the incremental form, like here in dx form. Because in dx form, I can make sense of the resulting random variable. I can find out the expectation and variance of the resulting random variable. So this is what we have done and why we have done this. So is this clear so far? So is this clear, or there are something which is not quite right? So I understand this is not very simple, even though we are working very informally, but you may need a little bit of time to digest this idea. So here I think is a good time to mention that, again, I want you to look at this MIT lecture notes, lecture note number 18, which is on ethocalculus. So how the ethocalculus is constructed, that is nicely explained in this lecture note, often quite informally. So this is something that you should go through as an additional material to whatever we are discussing. This would be a very good reference point to understand some of the nuances that we have been discussing here. All right. So let me just complete this part of the story, and maybe then we can reconvene later on when you have thought about this, read a little bit more about the background. So in general, we now know that writing differential equations, stochastic differential equations, in terms of the ratio dx dt is a bad idea, because we cannot have a candidate noise which will allow finite variation in the ratio dx dt. But we can write it as a formal difference expression using dx symbol, where we can make sense. So formally, we try to solve the following class of stochastic differential equation. This is a linear stochastic differential equation, dx equal to ax dt plus db. So this sigma dw we write as now in terms of the Brownian motion symbol db, where the variance of db is of the order dt. Informally, this is written as expectation of dv square is equal to dt. This is the Brownian motion. This is our candidate for noise. I cannot use the ratio form, but I can use the increment form with the Brownian motion. And there is another result here, which we are not explicitly going to discuss, which says that Brownian motion is the only candidate for noise, which will also give me continuous path property. So if I want whatever assumptions I have taken, and I want to make sense of this stochastic differential equation, then Brownian motion, this dB, is the only candidate for noise. Just like for a lot of nice results in our regression literature, we wanted the error to be normally distributed. For a nice stochastic differential equation literature, we want a Brownian motion increment as our model for noise. But as I said, this is not the only possible model, and life is not always this simple. Sometimes we must also allow for other sources of randomness. And this is one possible model. So this is a model with jumps. So I'm just going to mention this here. This will be taken up later on, actually as part of a special lecture later, where the processes with jumps in financial maths will be explicitly discussed and how to handle it to some extent. For now, I will just say that there are certain commodity prices like gas and electricity prices that exhibit certain jumps, and jumps are discrete, so they cannot be modeled using the normal distribution. As you can see that we have already have a nice structure here with the Brownian motion. So one way of modeling such processes would be to allow for a discrete jump along with the other continuous error process. So this is one popular model in the gas and electricity market. The log price of the stock in the differential form is modeled as, this is our mean part, which is actually a mean reversion process, dt, so that's the trend. Then I have this sigma dz, which is the error part with the normal continuous Brownian motion type of error, analytically nice. But to accommodate for jumps, to accommodate for jumps, I also add an additional term for error, which is a Poisson process, dp, that generates the actual jumps. And this is a discrete source of error. And if this Poisson process is known, then we can use some kind of binomial tree-based models to solve this kind of equations and then go on to do the statistics here, or we can do simulations. But there are also analytical methods, and some of the analytical methods will be discussed later on in the course. But for now, it suffices to say that we will, for some time now, we will only work with this sigma dz part, the nice Brownian motion source of error, and do the corresponding integration, etc. But there is an more general model which allows for jumps in the financial asset prices. Okay, all right. So we were here. So again, let me repeat my question. So is this construction clear to you? At least, are there any obvious problems? I understand that you need to go back, revisit, but is it roughly clear as of now?
Yes, sir.
Yes, sir.
Yeah, so I understand that this will take a little bit more time to get it through, but if you are clear about the basic premise, why we are doing it, we want to have some nice properties, but we also need to have a consistent model for all the calculations, then I think it should be reasonably clear to you. So then this would be our objective model, dx equal to ax dt plus db, and we will do the corresponding integration directly. I know that I do not want to write this ratio form. I want to write this as a incremental form, as in here. So what would be the corresponding integration that I want to define? The corresponding integration would look like this equation 4. So if I just simply formally integrate both sides, dx fxt dt and sigma xt dw, where dw is now our candidate db, then this would be formally the expression that we want to look at. So xt will be x naught. So basically dx integral will be xt minus x naught. So xt equal to x naught plus this ds integral, which is the usual integral, Riemann integral. So no problem here. I know how to do this integration. There is a second integral, however, which is sigma dbs integral. And this sigma dbs integral is something that we need to define. Okay, so now the need for the day is, we have come from the original differential equation to a incremental equation, a difference equation here, like if you want to call it that. And I can invoke the normality assumption here without any problem. I have this dB term, the Brownian motion term. So my differential equation can be solved by a formal integration process. That formal integration process now involves two terms. One of them I understand, but the other one we need to now define. So our next task would be to define this stochastic integral. Because if I can define this stochastic integral in a consistent way, then I have solved my differential equation. Because you see, if I can evaluate this whole of the right-hand side, then I know xt. And that is the solution to the stochastic differential equation we set out to do in the beginning. Okay, so I think I will stop here, because the development of the integral should be done in one installment, and today we have very few minutes left. So if you have any quick question, I will take that. Otherwise, we'll stop for today.
So you told about the jumps that are that often occur in the financial markets,
Yes.
and the analytical tools to approach them. Uh, is that do we consider only jumps that are independent of each other, or self-exciting jumps are also, like the Hawks process kind of jumps, are also considered?
Okay.
Uh,
So the first step was having a financial world with no jumps. And there we are trying to learn the integration theory, which will formally lead to the Black-Scholes model. Then we will introduce a very nice kind of jump like this Poisson processes, initially with full independence and everything, and try to see whether analytical solutions are possible. This was the literature till say about 5-10 years back. I think 5-6 years back. Very recently, we have just started to understand whether we can have correlated jumps, non-independent jumps. But the properties and the corresponding analytical solutions are still in a very nascent stage. So I do not want to comment much on that right now. But if you are interested, there are 1 or 2 recent papers which have come out on co-jumps, correlated jumps, which you can look at.
So the main reason I was asking this question, because I was going through the Hawks process kind of things, and that seemed to like model the scenario much better than the independence. So that is what the source of the curiosity was.
Yes, of course. But if you are going through that, then you also know that how difficult the analytical solutions are.
Yes, yes. So that I am not exactly familiar with what the current status of the literature is. So that is what I was asking that.
The,
Whether that
the current state of the literature is still very rudimentary. Only for very special cases we have analytical solutions. People still rely on large-scale simulation type of exercises.
okay.
Any other questions related to what we have done so far? Okay, all right. So I think